Alright, so in today's video we're going to be looking at this current donut Watchdog widget I made for this client across the pond. And so his application requires monitoring the current on a few lines, right? AC current, of course. Yeah, and so basically what he wants to do is if this current varies by a certain amount, either up or down, he wants to cut the power to a particular piece of equipment. And saw my previous video on the current monitoring donut, and yeah, so asked me to do this. And so this is how it looks. Has a little label on it. It's pretty prototypey, so this technically is going to sit in a pretty vibration intense environment. So I'm really not happy about the wires inside, right? You can see them wiggling crap, so that's... Anyway, but for a first prototype, that's fine, and you can gunk them down later, right? But now for the purposes of this video, it had to look pretty nice, so yeah. Let's actually take the covers off and have a look inside. Alright, so... first off, we have the main supply, right? This is going to go in the US, so I'm not going to supply this this flex with it. But yeah, it's just a regular one-phase input, kind of. Or is it two-phase, actually? Yeah, technically, it's one phase. Right? The ground is the ground, right? The neutral. Anyway, so I got this pretty schmick Meanwell supply. It unfortunately has this silicone here, so the purpose of this is to keep it from rattling around. The case actually comes down really close to it. So the case comes down really tightly, and yeah, so that was quite fortunate. This is pretty cool. I mean, it wasn't insanely expensive. I think I paid like 15 euros including shipping. 12 volt power supply, it's adjustable, has quite a long range, quite a large range, so it's like 10 to 15 volts or some shit like that. And then the rest of the stuff I think I'll go over with the schematic, right? So we have an Arduino. Unfortunately, I couldn't screw this down, so I have ordered some breakouts, right? There's these boards with like M3 screws that the Arduino would just sit in. And that's pretty cool because that way you can actually swap them out if they break and shit. So would have been very desirable in this case, but yeah, didn't have them, and yeah, it's gonna take another month for them to get here. Yeah, what else do we got? So we have the Arduino. It's controlling this relay and the two connections, right, to the contactor, right, that supplies the whole piece of machinery, whatever that is on the normally closed contact, right? And when this is made aware of any anomaly or something, it goes into a alert state, changes the color of this RGB LED. This is one of those digitally controlled ones. I forget the name, but I'll link all of the stuff in the description. So makes this blink red or some shit like that, and energizes the relay, which basically cuts this off, right? And so the idea is to have, right, you can see there's this arrow here, so have the 24 volt contactor supply come in here, then go out this way. There's also a tiny voltage divider here, complete with an industrially sized Zener diode, so 5 volt Zener diode. I've calibrated the resistors for this to go up to like 30 volts or even a bit more, but in case there's any spikes or anything, right, I don't want that upsetting the ADC on the Arduino. And so yeah, so that's why the diode's there. What else? Yeah, so basically energizes this, and I have a 12 volt supply which gets fed directly into the Arduino that has a local linear regulator. So that's going to provide a super smooth, super precise 5 volt rail. And then to not have the ADC readings being upset by this this relay, right, which by the way uses I think 140 milliamps, so that's not insignificant. I have this also powered directly from the feeding onto the main 12 volt rail this supplies, and being down converted to 5 volts by this switching converter, right? These are beautiful. I use these for absolutely everything. So you just pop off this potentiometer here with like a pair of snips or something, and then solder the connection you want. And they're super good. They go up to 30 volts. They're spec'd up to 24, but they easily go up to 30. Super low quiescent, super efficient, beautiful. Short circuit protection on the output. Enable pin, like all you could ever want. Anyway, so yeah, the relay gets supplied via the switching converter, and the Arduino and all the logic gets supplied by the linear regulator that's on board the Nano. Yeah, that's pretty much all. So we could basically, although by now it's rather pointless, I made it, so why not? So this is kind of roughly part of the wiring diagram, right? So we have one of the wires, right? Let's assume it's the hot, doesn't matter, right? We have this current donut on it. By the way, let me bring the current donut in shot. So we're going to be using a more robust current donut. So this is actually rated up to 5 amps AC. And we're going to use, I think, something rated to 25 or 20 amps. So there's these like a lot bigger ones with for sure less turns and like a bigger hole. But anyway, this is pretty good for the purposes of this test. They should all work the same, right? They just have an op amp boosting up the signal of this. I'm not even sure if they have an op amp or anyway. They just output a rectified wave, right? And I hope, right? I'm pretty sure they do though. Are there any diodes here? There's actually no diodes here, but I think the op amp does it. Like, I don't know, I've never looked into them. Anyway, and so these go via these, what are these, Molex connectors? And this was, in hindsight, is actually a very stupid idea. So especially in a super high vibration environment, I mean, you could plug them in and then hot snot them in place. But yeah, this was a lot of work and not super worth it. But I mean, it's pretty nice to have these modular, right? So I'm gonna unsolder this and ship the shit with the wires, and the guy has the donuts already, right? And yeah, so this is basically the current donut. Let's actually zoom in a tiny bit. Current donut goes into the ADC, microcontrollers in this case, and Arduino Nano. Then we have the 24 volt supply for the contactor that goes through our unit, right? Our unit has a relay that can break this connection. Something that's rather unfortunate, this input is polarity sensitive because we're also taking this measurement, right? We're also checking whether this contactor is energized or not, right? So with that resistor divider, right? So if we connect that the wrong way, we're gonna have a negative voltage on our ADC, so it's not too good. And as far as the operation goes, this is roughly kind of what ended up happening. So initially we have just some weight, right? In this case, I think it just blinks the LED in all the colors. Checks whether the contactor is supplied, right? Makes sure that the contactor is indeed energized, right? So not just one reading above a threshold triggers it, right? We need a certain amount of time. We need the readings to be above a threshold for a certain period of time, right? If no, we just sit here. If yes, we go to the next one. Here, the initial idea was to wait for all the inrush to go away, right? For all the machinery to get up to speed and stuff. But this is pretty redundant given that we spend this much time here, right? So anyway, because this technically will be supplied from the same rail as the rest of the machinery, so they will start at the same time as far as I'm aware. Anyway, you could add, like, there's a different state here, you can add a delay here or some other functionality. We're gonna look at the code in a tiny bit. Then we measure, right? So this is basically where all the magic happens. I made a little library. It's pretty dodgy, but I mean, does the trick superbly, I would even say. Right, it's just gonna be a number from 0 to 1023. And we could just say, if the current measurement donut, like measurement 1, or like motor 1, like give it a name. If that is less than 500, then yeah, not good. So we again have this kind of a yeah, safety check, let's call it, for lack of a better word. So if we have a measurement that is out of bounds, first of all we record a strike, I think I'm calling it. And if we get to 10 consecutive strikes, right? So if the current has, let's say the motor is completely jammed, so it's drawing an insane amount of current, right? 10 current measurements, I have no idea how much those would take. Those would probably take half a second or 5 seconds or 10 seconds or something like that. You can, everything is parameterized, so you can, right? He'll check the values and change this kind of stuff on site, right? I can't actually check it right here. So yeah, if basically the current is for sure out of bounds, then we get into this cut the power state, blink the LED in red, and on that matter, actually, just a little side note, if you guys are working on anything that, pretty much anything, right, that involves an Arduino and like wires and shit, I really would recommend making one of these wires, right? So basically what this is a Schottky diode on the plus rail, I think it is, accompanied by a bunch of resistors, right? And what this does is, I don't remember the values exactly, but if I were to short out this output completely, I think I've set the current to be about like 400, 500 milliamps. So that's for sure not gonna fry my Mac. And the Schottky diode, of course, prevents like voltage from leaking in. I mean, Macs have 2 USB ports, which is insanely little to start with. Fuck one of those up and yeah, you're dead. You're done. And so yeah, this is why I always use this kind of shit for this kind of project. It's pretty easy to make, so I definitely, and can save a lot of stuff, right? And so, yeah, so going away from this, I think we could wire this up and take a look at the measurements it's spewing out. Actually, I think we'll quickly go over the code first and then take a look at the measurements. So let's firstly connect the sensor. So I'm going to plug this in, right? This is basically just taking one line out and plugging it in. So as I said, right, this is has provisions for 2 current donuts, but yeah, could be as many as the analog inputs on the Arduino Uno, technically. Arduino Nano, sorry. Alright, so let me bring the laptop in and I'll be right back. Alright, so taking a look at the code, initially there's a shit ton of defines. I tried to format this as best as I could, right? Make it as readable as possible, right? Because the client asked me to make the stuff as comprehensible as possible because he wants to further develop it and stuff. And so yeah, so that's why all the formatting and stuff. And you can already see, right? So I'm including this library, and this is the one I created. So let's quickly take a look at the code for that. Okay, and this is how the library looks. So on the left we have the header file, and I have a bunch of constructors, so 2 of them. So you can create a current, let's actually make this full screen. You can create a current donut object with just defining the measurement pin, right? The analog pin, in this case it is A0 and A1. And this is exactly what I'm doing, right? So current donut, we're giving it a name, compressor current, and just calling it, giving it the pin, so compressor donut, and compressor donut is defined over here. So yeah, so this is A0, right? I've also provisioned, right, another constructor where you can also specify the sample count, and this will become apparent a bit later. And then basically these are the functions that we will be using. So is less than, right, is more than, and this is referring to the current, right, in relative terms. So if the current is less than This, it will return true. If it's not, it will return false. More than, same, is around. So basically target and band. It's also pretty intuitive. I've also made this, which is kind of a wrapper because it just looks nicer and I need it in the code, and why not? This is also pretty cool. So whenever one of these functions returns false, the counter, an internal object counter, right? So compressor current, this object has an internal counter which keeps track. I think it's even like a 32-bit one, is it? Sample count, no, 16. But anyway, no, wait. Current faults, 32, right? So you can record like 4 billion, billions and billions of strikes, of current faults. And you can retrieve them with this, and I do it when I'm in this error state and spewing them out. Set sample count is basically if you want to separate the functionality of this constructor, right? Just do it, just give it the measurement pin, and then later tell it how many samples to make, and this will become apparent a bit later, what the sample count does. And the last thing is just set the verbosity mode. So off doesn't print anything over the serial, so this is how the thing will operate normally, but during setup you might want to have more stuff coming out of the serial port. And so full prints out tab separated values for minimum, offset, and maximum, right? And this is what the sample count is basically. You take sample count number of measurements, compute the minimum, maximum, and the difference between them, right? And the difference between them is kind of the current, right? Kind of an approximation of the current that's flowing through this wire, right? Given that it is AC, right? We assume that we'll catch a peak, a positive peak and a negative peak, and then the offset technically is the current, right? Ish, again. Offset just prints the offset, right? These are the internal variables and a private function, kind of. And so basically this is what does all the work, right? This acquire readings function over here. And this basically just sets a minimum maximum and basically just reads this many like data points, right? It's just an analog read of the measurement pin, which has been set over here. Right, it's set at the start. So in the constructor, right, this dot measurement pin is this variable, and measurement pin on the right side is this one, right? So this variable gets passed on to this one over here, right? And that's pretty much all, right? Just maximum and minimum computing, right? You do this kind of shit in 5th grade, and just offset. And then, right, given the verbosity mode, we print, right, various information, and then, these less than, more than, these don't do a lot. Is around does perhaps a bit more, but again, not a lot. Is not around just returns the opposite of this. As I said, it's just a wrapper. And set sample count and verbosity mode, again. Although verbosity mode, right, a little gotcha, this also initializes the serial communications, right, because I'm not doing that in the setup. Right, what else? So yeah, these are the variables. I'm not gonna, right, I also have this NeoPixel LED. Super bright, pretty cool. What else? Mode, right? Maybe we could talk about the mode, right? Something that I'm constantly very proud of is setting the mode thusly, right? Just have the bits go 2 by 2, right? So assuming 1 bit flips, we're not going to end up in a different state that's going to cause like a lot of headache, right? Because if you just number them 1, 2, 3 or 0, 1, 2, 3, 4, then 1 bit flip, if it's in the lower bits, might actually take you to a different state. In this case, if you need 2 bit flips, this is already becoming super unlikely, right? Because to go from via an external bit flip. To go from state 0 to state 1, you need 2 bit flips, and you need the 2 bit flips to happen here and not here on the left side or anywhere else. So yeah, this is it's pretty cool. Compressor fault, this is also right when we discover a fault, we're basically ORing it onto a fault variable, right? So fault type is 8 bits, so right, it's this size, and we're just ORing this stuff, right? So if we just have a compressor fault, fault type will look exactly like this. Will be 4 zeros, 0, 0, 1, 1, right? If we have a fan fault, it's going to look 0, 0, 0, 1, 1, 0, 0. If we have both faults, right, well, or all of them, so it's going to look like 0, 0, 0, 0, and 1, 1, 1, 1 on this side, right? So this is how you can trace stuff back. This is, I've seen this implemented a lot of times. This is the first time I'm doing it. So again, all this stuff, right, was done pretty in a rush. I don't know, right? So I might have violated some sacred conventions and stuff. Like you'll have to excuse me. All right, so basically this again explains what the verbosity modes are, and this is already written up, right? So you could just easily comment stuff in and out, don't have to write it. Initial setup, basically just some NeoPixel stuff. And max brightness is something you don't want to leave at 255 because it will burn your eyeballs out, right? So. And output pin initialization, right? This is very important. If you don't, you somehow forget to implement, to write, to specify a pin as an output pin, it will still work, right? You can still say digital write, contactor supply relay high. And if you put your multimeter on it, you will see it go up to 5 volts. However, it will have absolutely no driving force. Right, so any amount of load, even the transistor from this relay module, will be enough of a current drain to drop that down to like almost 0. So you definitely need to define this as an output, otherwise you lose like half your life trying to figure out what doesn't work. All right, so next up we have the main loop, right? So this is basically the code that gets executed over and over again. Looks like this. And basically we have one of these if-defs. And what this does is if we have defined test mode here, it doesn't matter how we define it as, we could just define it as XXX or 5 or 9, you get the point. If this variable is defined, then this piece of code will actually get computed, will actually get read by the compiler, interpreted and processed. And so basically this is pretty much a while one, so an infinite loop, and basically now we have an infinite loop within the infinite loop. And so basically what this does is just reads, just asks if the compressor current, and this could be the other one, the fan current, just asks if that is less than 1024, which it'll always be because the range is 0 to 123, so it's just a 8-bit value. No, it's a 10-bit value, sorry. Is it? I think it is. Anyway. And so basically is less than, where is it? Is less than, right? What we're using this for is for calling this function basically. This piece we don't care about, right? The result will be thrown away. However, this acquire readings will execute all of this stuff here, and what we are actually interested in is this part, which actually spews out the values. So this is how we're using the verbosity mode, right? Also a little reminder, right? I don't want to have to set the verbosity mode every time, because the problem with that is this will initialize the serial interface multiple times, which is actually not good. This actually bricks it. So if you call serial begin without calling serial end before, it actually fucks it up. We could have another state variable and keep track whether we initialized it or not, but I mean, ain't nobody got time for that kind of shit. So I just put this commentary in. Right towards the end, right when stuff is almost done, right, this kind of hindrances just gets to be too much. And yeah, so basically, if this is not defined, we go over the little finite state machine which I showed on the page, right? So this basically just cycles the LED, goes into the next mode. I just define some random colors, and yeah, the rest of the stuff is not really worth going super deep into. This is basically just if the analog reading on the power thing is greater than the contactor threshold, which in this case I've defined as 0, and I've put a little like flag type commentary. So this needs to be changed, but when we're testing it, I don't want to have to actually hook up 24 volts to it, because yeah, again, ain't nobody got time for that stuff. So basically, if we see that the contactor voltage is present, we start this for loop, and what this does is it takes 500 readings every 10 milliseconds, and if one of them is not above the contactor threshold, it's going to break out of this, right? So it's going to come over here, and then the main loop is going to come again, and it's going to ask again, is the thing above the threshold? So we basically need 501 readings of the contactor threshold to be higher than contactor power threshold in order to go to the next mode, right? Because in each loop we ask, like, have we gotten to the end? If we have, then it means we have read 500 readings that are actually bigger, right, than the threshold, so we can move on. The contactor is clearly energized. It wasn't a fluke. It wasn't just a spurious reading or some shit like that. All right. So we go into the inrush wait, which actually, in hindsight, is redundant, right? But yeah, why not? Anyway, I've left it here. We could just put some other stuff here. This basically just takes it on to the next mode, and this is basically where the actual magic happens. So the LED is set to green because yeah, that's a good working condition color. These two, this is not good coding, right? Just having two pieces of code that look exactly the same. Usually if you have that, it's pretty bad. Again, this was close to the end. And it makes it a bit more readable, right? So I could have had all of this in a function, but then it would have been less readable, right? Which is again something that is quite important in this application. But anyway, right? It's yeah, people will not die. Is how I estimate this to go down. Anyway, so we ask if the compressor current and then the fan current, so we ask if the current is not around the target and the band, right? And if indeed it isn't, right, we set the the LED to yellow, so we show this to the outside world, right? We signal this because this won't always be connected to a laptop. And we initialize a strikes variable, and then start counting, right? So then we do 10 more measurements, and we ask the same thing, dude, is the reading really not within bounds, right? And again, every one of these calls will actually perform sample count readings, right? Which by default is 100, right? So we take 100 measurements and compute this offset, this maximum offset. If this is not looking good, right, it's a bit too much or it's a bit too low as well, right? If the fan dies or whatever the compressor is here, if somehow like a fuse blows or some stuff, you don't want the other one to run. Is basically what this entire thing this entire watchdog is supposed to guarantee. All right. And so yeah, basically we have 100 measurements that tell us, yo, something's off. Then we take another 1,000 readings, basically 10 times 100. And each time stuff doesn't look too good, we go up, we count up the strikes variable, which has been set to 0, right? Every time we get here, right? And so if we have 10 strikes, that means that we have 11 calls of this is not around function that have all returned true, right? 10 times in a row, 11 times in a row, has our current reading not been in bounds, right? So in this case, like, fuck this shit, this is bad, like, this is for sure bad, right? So we go into the failure mode, right? Into this trap state out of which we will never get out of without a reset. And we bitwise OR the compressor fault flag onto the fault type variable, right? So it's exactly what I've explained before. So this fault type will initially be zeros, right? And so we'll just OR onto this, the particular fault, right? Where were we? Yeah, over here. And that's pretty much all. And then we also check the other one, right? Because you could have like simultaneous faults on both. So why not do the same thing over here? And we also OR the fan fault onto the stuff. So yeah. And then we get to the like fault state. Set the LED to red. I mean, that's clearly the correct choice. We activate the contactor, right? So definitely, like, energize the contactor is basically what we're doing, but this could be the other way around. Like, doesn't matter, right? Usually you would expect a failure to not occur, so you don't want the relay being energized all the time. Yeah, why not? Because with the relay not energized, the whole system will use what? Probably 20 milliamps at most. Let's call it 50. With the relay energized, it's going to use 200. So 150 plus 50. So yeah, anyway. Exactly. So I have a 10-second. And the way we could test this, for example, is with a little fan I have. So let's first of all bring up the serial monitor. Why is that not showing? Also, let's use the other one. So these clones of Arduino Nanos use this CUH or CH, whatever it's called, this stupid serial chip that's way cheaper. And so this doesn't recognize the stuff. So anyway, this would be the... so I'm going to put the screen on the left side and just have the stuff on the right. So let's shrinkify this in case I'll need to cut some off. Alright, so this is basically the residual reading with absolutely nothing passing through, and let me actually bring the fan over and we'll take a look at how these readings change. Alright, so I have this fan, and let me see where I can put it. So let's take the widget out of shot and bring the fan in. Hopefully this is not going to end super badly. Let's plug it in, turn it on. Okay, so let's start the fan. Let's bring it up to 1. Bring it up to 1. You can see there's a tiny bit of inrush. If we take a quick look at that, right? So 146, and then it drops down and stabilizes to its values. Is this really 128? Yeah, so it's pretty stable. This is about 30 watts, I think, and each no, actually, what is it? So 4, 5, 15. So this is 35 watts. Level 1, right? We take it to level 2. And we get a reading that is not off by a lot, but this is actually 5 watts. So this gains, grows in power. There's different windings on this motor. And so they go up in increments of 5 watts, up to 50 watts on the 4th and highest mode. And so we're going from 128 to about like 140, 141. So this is definitely detectable. 139, right? It hovers a little bit, right? Just due to the nature of these readings. And by the way, so if you want to see the actual graphical representation of this, would be this, right? So this is on the bottom is the offset, and here we have the maximum and the minimum readings. And you can see now they're pretty close because we're not registering any current. This will auto scale once it gets to the end. And we start it on, right? You can see the maximum and the minimum come apart, and the difference between these is the height of this, right? And we take it to mode 2. mode 3, mode 4. Right, so you can clearly see what mode we are on. Right, we have some spikes, so these will definitely trigger, like we have definitely recorded one of those current faults over here, but didn't go into this protection mode because we really shouldn't, right? So this happens when we go from a higher mode to a lower mode. Actually it does happen when we go higher as well. So yeah, 4, 3, 2, 1, 0. 1, 2, 3, 4. And so yeah, this is pretty chill, I'd say, right? So 160 for 4, 149 for 3, 139 for 2, 127 for 1, and like something super low for 0. Alright, so today's tomorrow, and I figured out you guys wouldn't be too happy if I wouldn't give a demo of this actually working, right? Especially if we have the controllable fan. And so yeah, basically let's go for it. Just a quick side note. The thing started cold, shows these readings for these 4 speeds, and as it warms up it actually goes down by 10, which is actually the difference between these. So I don't have a lot of time because this will cool down, so let's start both of these up. Right, the module starts up, blinks the LED to show that all the colors are working with that superfluous blinker. By this time the fan has stabilized, all the inrush has gone away. We're checking if the contactor is present, which it is, and we're now monitoring, right? So we're actually reading the donut. It's actually spewing over the serial. I don't know if you can see the thing blink over here. Right, we don't have it connected to anything though. And basically I've set it up for step 2, right? So it's expecting the fan to be in position 2, which means it's reading 137, 138, 139, that kind of deal. And the band is 5, so even reading 142 would still be fine, right? Even 143 actually would still be fine, I think. I'm pretty sure. And so basically, let's right, if this works, we expect the relay to click if we change the speed, right? Either up or down. So yeah, pick a direction, and it's actually up, right? So we're down. Oh my god, this is just too much pressure. Anyway, let's go down. Right, so it's now reading the different values, and it has some hysteresis, which I've just programmed to be like 200 offenses, kind of. It was set to 10 in the code, if you guys remember, and that was pretty quick. That was half a second, which is kind of little. So let's see if it actually goes into the trip state, because if it doesn't, yeah, I'll have to re-record this, which I'm not looking forward to. Alright, so I did figure out what happened. It would have never triggered. So first of all, I've changed this. So this used to be 10 here. So the amount of false strikes used to be 10, and I've parameterized it. I've made it into a define, right? And put that first to 200. Unfortunately, the strikes variable was an int 8-bit. Right, and that goes up to 125, or no, 127. Sorry, how much does it go up to? So 2 to the power of 7 minus 1. Yeah, so it goes up to 127, and so yeah, it was just overflowing and never reaching the end. And also here it was equals to fault tolerance, and that's not actually correct, because this will actually get here to the point where it is equal to the fault tolerance and still add 1 on top. So when we're done with this, strikes will actually be larger, right? And so this was never actually coming here. and we were just counting strikes from 0 up to 200, 0, 200, 0, 200, and 1 actually, sorry. And so now I've changed it to 100, I think, to speed shit up, and I've also tipped the fan on the side to actually get the recording, and the readings are actually different, so these do keep changing. So given that we have such a small difference, right, of 5 watts between the different modi, right, we're definitely, this is not the proper resolution, right? So this donut is definitely under spec for this kind of sensitive application. If you have just a 40-watt fan, you probably don't want, or what you can do is just loop the wire a couple of times around the donut so you can get like more amperage read, kind of like more virtual amperage read. And so yeah, so the readings are all over the place. I have no idea why. So let's just center it around 122, which is what I read last time. And 138 was the reading I got initially. Ah, geez. Let's actually quickly just run a test mode. This video is going to take forever. But yeah, should be quite informative, I hope. So it's uploaded. Now let's open up the serial monitor, see what we're reading. So we're on step 2. And motherfucker, we're reading 92. Alright, so I have 93 here. It's going up. How the hell is it going up? 95, jeez. 96, holy crap, cut the shit. Jesus. Why is this going up? Is it cooling down? Like, what the hell? Alright, you know what? Let's just put 100 here and just have a big band and not muck around with these. So we're going to either have off compared to off or 4. Alright, so let's just give it, you see this is growing, so this is worrying, right? So let's just, fuck it, disable the test mode, right? So just comment out this. What do we say? 100. 100. And let's just give it a bigger band, right? Because this doesn't have the resolution for a 5-point band, right? You see it drifts all around. Like the air in the room gets cooler or hotter, it's going to affect the windings to the point where it's going to draw half a watt or 1 watt more or less, right? So that's the problem we're facing. So let's just go 30. We're not in test mode. The contactor is not being monitored, so this will always pass. And yeah, so this should work. So let's just upload the sketch. Alright, done uploading. Let's technically take this away because this won't be connected in normal operation. Alright, and let's unplug both of these and put you guys on the nice tripod and get like a proper shot of this working. Alright, so the fan has been running for quite a while now. Its current draw has stabilized around 100. And so the thing, well, we can reset it, right, to see its startup routine again, right? So just this LED cycling thing with the dimming. Let's let that finish. Now it's checking the contactor. The threshold for that is 0 at the moment, so it passes. And now it's in the monitoring mode, right? So it's showing green to show that the current draw is within spec. So 100 plus or minus 30. And for example, if we boost the fan up to from 1 to 3, so let's say somehow it draws more current, something's jammed in it, or like a bearing has failed, or who knows, right, something. So it goes to orange, and within a few counts, right, so we could actually bring it back down to 1, and it gets back to green, right? So this would be an intermittent fault, so the actual strikes have been recorded, right? They are now saved in RAM. But if, let's say, the fault continues, persists, right? We do want to shut the system down because something is off. And that is exactly what would have happened now, right? So if I had routed the relay the way it's intended to, it would actually cut the fan out, kind of, right? And then it doesn't recover from this mode, right?